on forced convection. So here, so this experiment is been related to forced convection, how the heat is being transformed in the forced convection. So in this experiment we are going to determine the convective heat transfer coefficient for forced convection through horizontal pipe. When fluid flows over a solid body or inside a channel, while temperature of the fluid and solid surface are different, heat transfer between the fluid and solid surface takes place as a consequence of the motion of fluid relative to the surface. This mechanism of heat transfer is called as convection. Convection heat transfer strongly depends on the fluid property like dynamic viscosity, thermal conductivity and density. Convection heat transfer is expressed by the Newton's law of cooling. This is Q is equal to H into A into temperature difference on surface, where H is the convective heat transfer coefficient, A is the surface area of the flow passage. So here we have been having that Ts, the temperature of the surface, and Ta is the ambient temperature of the air. Convection is classified as a free convection and forced convection. In forced convection, heat transfer, the fluid is forced to flow over a surface or in a pipe by external means such as in a pump or a fan. The heat transfer rate is high in a forced convection due to rapid movements of the fluid particles. So in our experiment we have been using the blower for the transfer of the heat. So now let us see the experimental setup, what are the things we have been having. So here it consists of a horizontal pipe fitted to the blower to achieve forced circulation of air through the pipe. So this is in a pipe. So inside this, at the bottom we have been having a blower, so which is being connected through the pipe. So here pipe is surrounded by band heater and 5 thermocouple. So here you can see, here also they have been having a thermocouple, and inside also we have been having a thermocouple which is not visible on surface. So here the temperature from T1 to T6 are fitted on the surface. In addition, 2 thermocouples are placed at the inlet and outlet of thermocouple, so which measures temperature T7, T8 to measure the air temperature. And an orifice meter is used. Orifice meter is used in the blower pipe to measure the flow rate of the air. Input to the heater is varied and controlled by the regulator. Here whatever the heat we have been transferring to the heater, that is been controlled and regulated by this regulator. So usually when you switch on the system, we are able to regulate this one to at a constant temperature or in a constant heat flow we have been maintaining. So here the procedure goes as follows. We are going to switch on the heater and adjust the regulator for required heat input. So first we are going to switch on this one, then for heater we are going to switch on this one, then afterwards we are going to regulate this auto transformer so that we could able to maintain a constant current flow in the heater. Then switch on the blower and adjust the flow of air using the gate valve of the blower. So here we have been having gate valve for flow of air to this heater. So here we are going to adjust that adjustment. The flow of air is being measured with help of this manometer. Wait till the steady state is being reached. Note down the voltmeter, ammeter and manometer reading. So note down the thermocouple readings from temperature T1 to T2. So here we are able to find the temperature T1, T2, T3. So at different thermocouples. And here we are going to repeat the experiment by varying the heat input and by varying the heat flow rate of air in the blower. So now look at the observation, what are the readings we need to take care. So before that we will go through the tabular column, what are the things we need to make a note of it. So here you can see a tabular column. In this tabular column we have been having a volts and ammeter. We have an indicator from where you can find out the volts and ammeter. From this you can identify what is a heat supplied, and you are going to note down the manometer reading. Okay, so where the water is been flowing or air is been flowing depending upon the situation what we have been using it. So then we have been having a wall temperature reading. So these are the from T1 to T6 we are going to note down. So at different thermocouple which have been placed on the surface of the heater. Then we have been having an to find out the ambient temperature, means that is an air temperature, we have been having an T7 T8. So that we can identify from the indicator. So then we have been having a heat transfer coefficient. Here the heat transfer coefficient we are going to find out through experiment way and the theoretical way. So how we need to calculate, let us look for the observation. So here we have been having an observation where the inner diameter of the pipe, that is D1, that is been given 36 mm, and the outer diameter of the pipe, that is outside surface, that is been given as a 42 mm. Then length of the hollow pipe, that is of a 500 mm, means what is the length we have been going to consider here. Then orifice diameter, that is 20 mm, so which the manometer is been connected. So then acceleration due to gravity, that is G, as you know it is 9.81 meter per second square. Then coefficient of discharge of orifice, that is CD, that is equal to 0.62 we have been taken. Then density of the water, we know it the standard 1000 kg per meter cube. The density of the A, that is 1.154 kg per meter cube. Then distance between two consecutive thermocouples T2 T5, that is 100 mm. Okay, these are the standard observation as the experiment is made to set up. Now we are going to calculate the heat transfer coefficient from the experimental method. So from the experimental method we have been having a heat input. So we have been from the tabular column, we know the value of voltage and we know the value of ammeter, we could able to identify. Then surface area of the flow passage, so you know the value of pi, you know the value of the inner diameter of the pipe, and length of the hollow pipe we know, so we could able to find out the surface area of the flow passage. Then surface temperature, we have been taking the average of 6 temperature what you have been calculated on surface of the pipe. Then air temperature we have been taking as an average, that is T7 and T8, which are been placed at the either of the ends. According to Newton's law of cooling, heat transfer coefficient, this is an equation we have been having. You know the value of the Q and you know the value of the area A, you know the temperature, average surface temperature and ambient temperature average. So we could able to find out from the experimental method what is a heat transfer coefficient we have been getting. In the same manner we are now going to find out the value for theoretical calculation. Here we are note down the properties of A for the average temperature, that for here the average temperature what we have been found out on the ambient temperature. For that one we are going to find out kinematic viscosity, density, thermal conductivity and Prudhon's number from the heat transfer data handbook. From there we are going to find out. From there the head of the air, we are going to substitute this value of density of water, density of air. Then we are could able to find out the HW is the head of water from the manometer reading. So difference of the manometer reading what it has been come. So we are going to put over there. So then head of the air we are going to get it. In the same manner the area of the orifice meter also we are going to find it. You know the value of the pipe and the diameter of the orifice we know. So we could find out the area of the orifice. Then discharge of the air in meter cube per second, that one we are going to find out. We are going to substitute the value of CD which is already been given and the area of the orifice, then root of 2 GHA. So HA, that is a head of the air. We could find out discharge of air in meter cube per second. So next we have been having the velocity of air also we could able to find out by knowing the area of the pipe, that is cross section area of the pipe. Then afterwards from the data handbook we are able to find out the Nusselt number by knowing the Reynolds number and Prudhon's number. Okay, so Reynolds number equation we have been got it. All the values what we got for the ambient temperature we are going to substitute it. So after getting all this value we are going to substitute this one in the Nusselt number equation, where the heat transfer coefficient can be calculated as H is equal to Nusselt number into thermal conductivity, then so inner diameter. By substituting this one you are going to get a value of heat transfer coefficient theoretically. So note down those values in this tabular column here, from the experimental what you have been got, from the theoretical what you have been got.